The central limit theorem is one of the linchpin theorems that we use throughout the study of statistics, and that's particularly true at the first year level. To illustrate the application of the central limit theorem, let's have a look at this problem right here. So we're talking about Rice Krispie bars. We're told weight in an individual package is stated to be 22 grams, and I'm just going to flick over here for a second. So I'm talking about one Rice Krispie bar, which you can buy sometimes individually or you can buy in boxes. Okay, says here the amount that the packaging machine puts into these bags is believed to have a normal distribution, so we're told that right at the get-go. The mean weight of all these individual bars is 22.2 grams, and the standard deviation is 0.4 of a gram. And we're told that some of the bars are sold in boxes of 24 bars. Okay, two questions were asked, both which have to do with probability, and both which have to do with probability of bars being below the stated amount. So the stated amount on the bag is 22 grams. We want to know in part A, what is the probability that the weight of one Rice Krispie bar, go away. What is the probability that the weight of one Rice Krispie bar is below the stated amount? And in part B, what is the probability that the mean weight of bars in a box of 24 is below the stated amount? Now, part A of the question does not require the central limit theorem because we're only picking one item out of the population. However, part B of the question is going to cause us to invoke the central limit theorem because we are taking a sample size greater than 1. So let's have a look at how we would go about answering these questions. So first of all, the first question is, what is the probability that one bar, and I've called that bar Y, what is the probability that one bar randomly chosen off the line has a weight less than the stated amount, which is 22? Now, I could work this out using z-scores, or I could use Minitab to get the answer. So, first of all, what do we know about the distribution of the individual population of bars? We know the mean weight is 22.2 with a standard deviation of 0.4. I could calculate the z-score on a value of 22, so I do that. I get a z-score of negative 0.5. And if I didn't have computer technology, I would go into my standard normal distribution tables and I'd find the area to the left of a z-score of negative 0.5. And that answer would be this one right here, which is approximately 0.309. Or, because I have technology available to me, I can go into my Minitab or something similar, specify a normal distribution, give it the mean and give it the standard deviation of the population, find all the area to the left of 22, and there's my answer for Minitab at 0.3085. Okay, so out of all of this, there's a 30.9% chance that if I take one randomly chosen Rice Krispie bar off the line, it's going to be below the stated amount of 22 grams. In the second part of the question is asking us what is the probability that the average weight of 24 bars is less than the 22 grams. So we're now talking about the distribution of the average weight in boxes of 24 bars. So I guess from a realistic point of view, what you would do to get this distribution, if you really had to do it from scratch, you'd go to your production line, you'd take off a box of 24 bars, you'd take all the bars out of here, you'd weigh them all, and you'd find the average of the 24 bars, and you'd record that average. And you'd go get another box of 24 bars, take them all out, weigh them, record the average, and do that over and over and over a large number of times. Well, central limit theorem says that, well, instead of having to do all that craziness, we could just look at the properties of the central limit theorem. And central limit theorem says the mean of all those averages, the mean of the means, the mean of my y bars, is equal to the mean of the population of individual bars, in this case, which is 22.2. but that the standard deviation of all those means is something smaller. And how small is it? Well, I got to take the standard deviation of my known population, divide by the square root of my sample size, and now I get a standard deviation of 0.08, which is significantly smaller than the standard deviation of the population. So when I go to do my calculation this time, and again, if I did it from a z-score, I now need to calculate a z-score on the sample mean relative to the mean of the means and the standard deviation of the means. Okay, so what's the probability the mean is less than 22? So first of all, y bar is 22. Central limit theorem says mean of my means is the same as the population mean, which is 22.2, and the standard deviation of all these means is given by sigma divided by square root of n. So working all this out, I get a z-score of negative 2.45, and again, if I had to go to tables, I'd find all the area to the left of negative 2.45. Or I can go to Minitab. And right up at the top here, so pay attention there, the mean is 22.2, but the standard deviation this time is something considerably smaller at 0.08165. And Minitab tells me that all the area to the left of a y bar value of 22 is 0.007. So now this probability is a lot smaller. So in this case, what are we looking at? We've got about a 0.715% chance that the average weight in a randomly chosen box of 24 bars is going to be below the stated amount. Whereas, if I go back up here for a minute, and I look at what was the answer using the population and picking one individual bar, that probability is 30.9%. So there's a big difference between the 30.9 and the 0.7%. And why is that the case? Let's flick down here. I have graphed both distributions on this one graph. The blue one here is the distribution of the individual bars, and the red one here is the distribution of the means of boxes of 24. And here's the stated amount at 22, and I can see there's a lot less area to the left of 22 under this red curve than what I am going to have under the blue curve. And we are going to be seeing central limit theorem over and over again as we go through the rest of this course.